Welcome back. This is the first quick video that I want to do on the concept of Lowry Bronsted acid-base theory, simply because there's so many nuances that you have to learn first before you can really venture and learn the concept in full breadth. Okay. Now, as I said, this is one concept. We'll be on it for a while. We might come back to Arrhenius again and then go back to Lowry again, depending on what we're dealing with at the time. But we're going to be shuffling back and forth between these two theories. But for a greater portion of the course, at least 1/3 of what is remaining, we'll be relating everything else we're learning back to Lowry Bronsted. All right. Now, again, you have to remember the 6 strong acids, and anything that's not on the list is weak. And for the purpose of Lowry Bronsted, you see that one of the reactant is always water. So you do not have to worry about so much of the strong bases, list of strong bases. You still have to remember them, but you see that one of the reactant is always water, and that's done for a reason. All right. I'll explain that as we get further into the topic. But this is kind of the intro video where we learn to write some expressions, learn to write some ions and stuff like that. This is kind of very, very foundational. All right. Now, there's a few terms that I want you to know but not memorize. Again, I will tell you only have to memorize, and that's not very often. And I've just said that in one of the introductory videos. You do have to remember the 6 strong acids. But you do not have to memorize these, but just remember them. CB stands for conjugate base. CA stands for conjugate acid. Ka stands for an acid dissociation constant. Kb stands for base dissociation constant. At least in this video, we're going to see all these 4 in action. All right, but before that, let's step back and remember what Lowry Bronsted theory is. Well, it's said that an acid it donates a proton, right? And a proton is H+. And a base it accepts a proton, right? Well, do I have to tell you, say I give you this reaction, do I have to tell you, again, you see both the reactants are labeled. Water is always liquid or gas or solid. Okay, it cannot exist as aqueous ever. Does that make sense? Okay. Water is used to make other components aqueous, but water itself cannot ever be aqueous. All right, you see I've labeled everything. So that's one thing you may not have to worry. But again, once you start Lowry Bronsted, it's purely one of the component is weak, and that's why you start to see these double-headed arrows. All right. Now, the first thing I want you to learn is how to use this definition to write the products. All right, so let me get a different color here just for a second. Maybe this blue. Oh no, just was using the blue. Let's use this. All right, so out of this 2, this is acid, okay, because it's called nitrous acid. It's HNO2. And so this is the acid, so write A. If this is acid, this has to be base, okay? That's the way it works. You cannot have acid, okay? This just makes no sense. This is base. If this is acid, this has to be base, all right? Okay, because as I said, water can be acid or base, but that's for a different situation. For now, this is nitrous acid, which is A. Because typically aqueous in this case is A, and this is B. So an acid donates a proton, right? So the proton from here goes to water, right? Because that's the way the definition says. Acid donates a proton to water. So how are we going to write the products? Now, first let's write the one without the hydrogen, but it's missing something. Okay, whenever an element donates a proton, okay, it's donated 1 hydrogen, so it's lost 1 hydrogen, but it's donated a proton, so this must get 1 negative. Okay, this is not same as losing electrons. Okay, this is lost a proton to this, so the NO2 should get a negative, Whichever one has lost the proton should get the negative. And how many negative depends on how many protons is lost. It only had one hydrogen, which is what is lost as proton, so it can only get one negative. Now, this is the most frustrating part is despite hundreds of hours of instruction, students write the formulas as they wish. Okay, now this is one thing that always gets to me is you cannot write unbelievable formulas. Okay, formulas that are never ever possible. Okay, so you've added a hydrogen here, so you write it as H3. The hydrogen combines with the hydrogen that's already there. Now you've added a proton, right? A proton has a positive charge, so the positive charge is now carried over by water. Because we transferred one proton, it's 1 plus. All this seems like rocket science. It's not, all right? You just have to do a couple more examples, and that's all it takes. All right, now this is correct. I have seen students do this. Please don't do this. I have no idea what this really means. Okay, this is no longer chemistry. This is, I don't know what to say, but it's definitely not chemistry. Please don't do this. All right, now if I see you, I'll just give you a flat out F in the class. All right, I will not even bother to grade the remainder of the exam if you write this. All right, so don't write this. Write something else besides this, because this has no meaning whatsoever. Okay, I've never seen anybody, this just violates a whole bunch of laws, and it just doesn't make sense. All right, so just don't do this. Don't write this unless you want an F. Just go ahead and write it. All right, or select that as an answer choice. All right, with that said, the one that loses the proton gets a negative charge. How many does it get? Depends on how many protons were lost. Here only one loss, so one negative. Only one proton is gained by the water because that's what the definition says. Acid donates proton, base accepts proton, right? This is the base, that's the acid. So it's accepted the proton, right? Now what was acid? It's now a conjugate base. I'm going to write this actually in different color. This doesn't take any kind of, again, you do not have to memorize any of this because that beats the whole purpose of it. If this is, whatever is acid, which is the NO2 component, this has to be a conjugate base. Because now this can accept a proton. That's what it really means. Okay, whatever is base is now a conjugate acid. Does that make sense? What it really means by double-headed arrow is once this is formed, now again, whether it's conjugate acid or acid, an acid is an acid. So it's going to donate proton back to this, giving you the HNO2, and when proton is lost, it gets water back. So all this can go back to this. That's what it means. In that, so that's why whatever you start with an acid will become a conjugate base, and whatever you start with that is a base is a conjugate acid when you make the product. Let's see how far you've gotten through. All right, I've said in my list of acids and bases, this is a weak base or base. Let's write it as just base. This is a base. If this is a base, this has to be an acid. Okay. Now, what is the theory states? An acid donates a proton, right? And a base accepts a proton. So the base accepts a proton. So write it as NH. Add the hydrogen to the existing 3, make it NH4 plus. Now, because in the previous case, when a base accepts a proton, it gets a positive charge. How many does it get? Depends on how many it gains. It gained only 1 proton from the acid, right? Now the acid has lost 1 proton, so it's only left with OH, right? It's lost one of the hydrogens to the ammonia, NH3. So if it's lost 1 proton, it'll get 1 negative charge. So this was base, so this must be, you guessed it right. This is conjugate acid, and this is conjugate base. Okay? Sorry, conjugate base. Now let's learn something that I really wanted you to drive from this. Okay? Lowry Bronsted is primarily with weak acids and weak bases. Okay, water is weak, nitrous acid is weak acid, ammonia is weak base, etc., etc. Right? So whenever you're dealing with an acid dissociating, we call it Ka, right? So if you have to write an expression which is called the Ka expression, all you have to do is, well, basically what dissociation constant is, it's a ratio of concentration of products over ratio of concentration of reactants. Now, if you're, this is something, one thing we have not done for sure, and that is concentration is written in square brackets. Okay, so what that is, so to write, this is Ka because we're starting with an acid. Okay, it's ratio of concentration of products over concentration of reactants. You will see, let's see if you pick up something that's missing in this expression. Okay, so it's 1 minus, that's in the product. If you still don't know which one is products, again, that's a red flag. You need to drop the course. Okay, this is products, this is reactants. Okay, and concentration of HNO2. Okay, you see I did not write water in the product. This is the way it's written. Okay, concentration, we could put physical numbers inside of it, but what I really want you to take away from this is NO2 1 minus and H3O 1 plus, that's on the product, divided by nitric acid. So only things that are aqueous can go. If the substance is solid or liquid, like in this case water is liquid, it cannot go in the Ka expression. All right, let's see if you can write the Kb expression. Okay, which is, if you're starting with a base and you see a double-headed arrow, you know it's a base dissociation constant. Okay, it's Kb equals ratio of NH4 1 plus. Again, you can write NH4 plus or, you know, write NH4 1 plus. They both mean the same. OH minus, and then divide by NH3. Again, I do not write water because you cannot write pure solids, liquids, and gases. In gases, not so much, but pure solids and liquids definitely don't make it to the expression. First, I want you to understand how to transfer protons and how to write this expression. Okay, you may have to watch this video more than once. I'm going to make one more video with 2 different examples. Let's see if you understand that. All right, once you're comfortable with moving proton, writing charges and ions, and labeling the appropriate, what I could ask you is, what is the conjugate acid of NH3? We know NH3 is base, right? So what is the conjugate acid? Well, you may have to do it this way, but down the road, you know, if you're base, then a conjugate acid is merely with a plus charge. Okay, this is conjugate acid. Now, some of you, most of you may have to start doing this way to figure out, if you're starting with a base, then whatever is base is, you end up with the conjugate acid. If you start with an acid, you end up with the conjugate base. All right, now I'm going to stop this here because I don't think there's a whole lot that I could say differently that would make you understand this any better, other than just doing another video with 2 more examples that would kind of reinforce this concept. So I'll see you back with another video.